is section 4.1 called the derivative and tangent line problem. We're going to start this lesson with remembering what a secant line is. So recall that a secant line to a curve is a line through 2 points on the curve. And right here below, I have a definition of secant line in terms of an expression. Let me draw you a picture of this slope, or of this meaning. And so if I have a curve, f of x, and I want 2 points on the curve. So the 2 points on the curve, I'm calling them c plus delta x and c. And those are the x values. So maybe this is c, and this is c plus delta x. And notice that these 2 points are the distance of delta x. They're delta x away from each other. So here's 1 point, and here's a second point on the curve. And so in order to find the slope of the line through those 2 points, which that is called the secant line goes through 2 points on the curve. In order to find the slope of this line, I need to find the change in y values divided by the change in x values. That's always slope. And what that means in terms of my notation here, where c is an interesting x coordinate, and a second point is delta x away, then my change in y values are going to be f of c plus delta x minus f of c over delta x, which is just change in y over change in x. If you can recall, we did this in section 3.1. We called this point P, and we called this point Q, and we made Q have a bunch of different x values. Okay, and this expression, the slope of the secant line, is so special it gets a name. It's called the difference quotient at C. So the difference quotient can be different for different x values, but it's the difference quotient per function f at location C. All right, what we did in 3.1 is we used that slope to estimate the slope of a tangent line. And so here we have definition of tangent line. The tangent line at a point is the line that goes only through the 1 point in the direction of the curve. And the slope of the tangent line is called the slope of the curve. And so if I go back up here to this drawing I have, if I want the tangent line at C, that would be this line here in blue. The blue line only hits the curve at C, and I've tried to draw it in the direction of the curve, so it just barely lays on top of the curve at that spot. So that's what I would mean by direction of the curve. It's not going to hit through the curve perpendicularly or run through it. It's just going to lay on top of the curvy part and only hit in one spot P. So that slope of that tangent line is also called the slope of the curve. It's also called the slope of the curve, and I'm at a specific location x. And we've been studying limits so far. The reason why we're studying limits is so that we can formalize how you find the slope of the tangent line. The slope of the tangent line is the limit as the distance between your two secant line points, delta x, right? As that distance, delta x, the distance between the 2 points right here, becomes 0. If this distance becomes 0, then I've moved my Q point so that it's closer and closer and closer to P. And so this limit, as delta x goes to 0, that's the slope of the tangent line. Okay, so let's do an example. Let's find the slope of the curve y equals x squared at 2, 4. I'm just going to write the definition down. The slope of the curve is the slope of the tangent line, which is the limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x. C is my x value, 2. So I'm doing the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 over delta x. At this point, in order to keep moving in my limit, I'm going to do some side work. And in my side work, I'm going to try to figure out what this quantity f of 2 plus delta x is. So what is f of 2 plus delta x? Well, in this problem, my function is always what y equals, right? F of x is y. My function is x squared. And so I need to take the x and x squared and replace it with the input 2 plus delta x. So that is going to equal 2 plus delta x squared, because y is x squared, and if I replace the x with 2 plus delta x, that would be f of 2 plus delta x. This FOILs to 4 plus 4 delta x plus delta x squared. So that is the end of my side work. I'm now going back to my limit. I'm doing the limit as delta x goes to 0 of, actually, let's do some additional side work too. Let's find f of 2. That would be 2 squared, 4. So for the f of 2 plus delta x, which I have, let me put it in purple here. I just did side work and figured out what f of 2 plus delta what x is. It's equal to this. And so that is going to be substituted into my limit. So I'm evaluating the difference quotient before I evaluate the limit. That's what's happening here. Minus f of 2. f of 2 was 4 over delta x. And so all I've done is I've written down the definition of my slope of a tangent line. The limit is delta x goes to 0 of f of c plus delta x minus f of c over delta x. And then I plugged in the 2 plus delta x in for this function x squared. And now you can evaluate this limit very easily because you have been working for a week or so on how to evaluate limits. So 4 minus 4, that cancels. And a delta x will factor out of the top. This was a delta x squared. So when I factor out that delta x, I still have 1 left. My delta x's cancel. There I'm canceling the 0 over 0 part. And so I can evaluate this limit. It is 4 plus 0, or 4. So I know that the slope of the tangent line to y equals x squared at 2, 4 is 4. So the slope of this very steep line is 4. Okay, here is a second example for you to work out. 2x minus x squared at x equals 1. Let me help you get started. So I'm going to write down the definition of the slope of the tangent line. It is the limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x. I just recopied that down from my definition. C in this case is going to be the location that we're interested in. That is x equals 1. That's my given point, x equals 1. Okay, so I'm going to replace the C with a 1. Now let's do some side work. What is f of 1 plus delta x? That would be 2 times 1 plus delta x minus 1 plus delta x quantity squared, because I've replaced the x with 1 plus delta x. Okay, this reduces to 2 plus 4 delta x plus 2 delta x squared. I did that wrong. I squared the wrong one. 2 plus 2 delta x minus, you'll have to FOIL 1 plus delta x. So that's 1 plus 2 delta x plus delta x squared. Don't forget to distribute your negative. All right, and then we'll collect like terms. I'm going to collect like terms as I plug it in. So my f of 1 plus delta x is negative delta x squared plus 2 delta x minus 2 delta x plus 2 minus 1 plus 1 minus, what is f of 1? Well, let's plug in 1. F of 1 would be 2 times 1 minus 1, 1. over delta x. And now I have delta x squared plus 1 minus 1. My plus 1 and minus 1 cancel. And I have negative delta x squared over delta x. Well, one of these delta x's will cancel. And I'm left with negative delta x. So if I evaluate that limit, I just need to plug that 0 into delta x and I get 0. So the answer to the slope of the tangent line here is 0. Here we have a third example for finding the slope of a tangent line. I'm going to do the limit as delta x goes to 0. Notice here the c value is 4. C is always an the x coordinate of the point in question. So f of 4 plus delta x minus f of 4 over delta x. Here's my difference quotient. With c it's 4, and now I need to replace the 4 plus delta x into the x in my function. So that's going to be square root of 4 plus delta x minus f of 4 is 2. That was actually given to me this time. Over delta x. Now, if you replace delta x with 0 here, you'll get 0 over 0 indeterminate. Why don't you pause the movie and pause these notes right now and finish this out for me. When you get 0 over 0, that's indeterminate. That means work harder. So this is a good practice to see if you can work harder here. What is the strategy you should do to try to evaluate that limit? I'll tell you, I think the answer is supposed to be -1/2. You can tell me if I was right or not. Okay, I have another example here. And look at this example. In this example, I want to do it at 2 points. 2 points. That's ridiculous. I'm sick of it. I'm sick of doing that difference quotient limit over and over and over again. And in this example, it's the same function. So I'm going to try to develop a formula for this. Let's do the limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x. Well, let's not specify which one of these two numbers is c. Eventually, they're going to have to be both of them. But I don't want to do one, and then I don't want to have to go back and redo it all over again for -2. So I'm just going to keep it as c. Now what does my side work look like? What is f of c plus delta x? Well, it's 3 times c plus delta x quantity squared plus 2. This is 3 times, if I FOIL c plus delta x, it's c squared plus 2c delta x plus delta x squared plus 2. And then you'll distribute the 3. So let's put that into our difference quotient limit. We get 3c squared plus 6c delta x plus 3 delta x squared minus, and then if I plug c in, I'll get 3c squared plus 2. Don't forget to distribute the negative here. Getting messier here. Okay, 3c squared minus 3c squared. I forgot the plus 2. See him? It's supposed to be here. Plus 2 minus plus 2. And I'm only left with 6c delta x plus 3 delta x quantity squared over delta x. The delta x will factor out and cancel. You're going to get really good at doing these because you are going to do a bunch of them. And so you get 6c plus 3 delta x once the delta x was factored out and canceled. So if delta x is 0, that's this part here. That's going to be a 0. I get an answer of 6c. And now it's much easier for me to answer this question. I don't have to do 2 limits. I did 1 limit, but I made it a formula where I didn't specify c to be 1 or c to be -2. So my answer is the slope is 6c. That's what I got. So when c is 1 at this point, my slope of my tangent line at 1 is 6 times 1, or 6. And then the slope of my tangent line over here at -2 is 6 times -2. That's -12. So that was a much better way of working this out. I got to do only one limit, and I could find the slope of the tangent line at any place in question. This is called a derivative. So the slope of a curve is the slope of the tangent line. That's the limit of the slopes of secant lines. And that is this difference quotient right here. Except I've done something. I haven't used c. What have I replaced c with? I've replaced c and I've kept it the variable x. Because what I'm doing is I'm finding a formula for the slope of the curve at any x value, not one specific number. This is the derivative. And you are studying calculus, and the very first thing that most people remember about calculus is derivatives and differential calculus. So here I have it written again in a nice big box, the definition of the derivative. Then down here at the bottom, I have some notation about what it means to have a derivative. Remember, we've done a lot of limits that don't exist. So we're assuming a limit will exist here. And if a limit doesn't exist, then the derivative doesn't exist. But when the derivative exists, this is f prime of x. If f prime of x exists, then the function has a derivative. It's differentiable. All right. Now we have to discuss some things here. It turns out that there are two discoverers of calculus, Isaac Newton and Gottfried Leibniz. Gottfried Wilhelm Leibniz. Leibniz was German and Newton was English. And they discovered calculus right at the height of, well, during at least, English and French tensions. England and France used to hate each other. This was right around like Napoleon. And so we're talking about, I think, just after Napoleon here. And so Newton and Leibniz hate each other. And they don't hate each other, actually. They're both mathematicians. But Newton studies in English, in England, in London, at Oxford. Actually, I think when he discovered calculus, he was at home because of the Black Plague. And no, that's when he, anyhow. Leibniz, however, studies in Paris and France. And they're both mathematicians, and they did consult at some point. And after that consultation, Leibniz publishes a paper describing like the beginnings of calculus, and it's this major breakthrough. And then Newton gets very mad because he claims that Leibniz has taken his ideas and published them, and that Newton really contributed most of those ideas. And so Newton publishes his paper about calculus and claims that even though he published his paper after Leibniz, he actually thought of the ideas first. So there's a big controversy over who should get the credit, and this continues throughout all of the tensions between France and England. And so as people are starting to study calculus more and more when this discovery occurred, you kind of pick a side, and based on whose side you pick, you write things differently. As a result, we have about 1 million ways of writing the same exact thing, and that's what this page here is about. All of the different ways that you can write the derivative. At this day, today, we give both of them equal credit for discovering calculus. But you also get to write in both notations. There are benefits to each one. All right, so what I have here is y equals f of x. That's my original function. F prime of x, this is the derivative. F prime of x. So we say the words f prime of x. So this is the derivative. And this would be Newton's notation. The primes are Newton's notation. Right here, or y prime, right? Because y is f of x. Those mean the same things. The outputs are f of x's or y's, so the derivative is f prime or y prime. Leibniz notation is this dy dx. Okay, so it looks like delta y over delta x, doesn't it? And that's what it is as delta x approaches 0. That's what delta y over delta x becomes. It becomes what we call dy dx. It's the derivative of y with respect to x. This notation is Leibniz's notation. It is better sometimes, but you have to write more. So most people don't use Leibniz's notation unless they're doing the problems in which it's easier to use it. Again, you could replace y with f and call that df dx. And here you d dx f of x. This means the derivative with respect to x of f of x. This is also sort of like a verb. D dx is differentiate with respect to x, f of x. And then there's another notation down here. I don't see it very often, but it means differentiate with respect to x, y. So all sorts of notation for the same exact thing. All right, so I have two functions here, and this is my last example. These are my last two examples, and we're going to find the derivative. So we're going to find g prime of x. And in order to do that, I'm just going to write down what the definition of the derivative is. So g prime of x, by definition, is the limit as delta x goes to 0. My function's name is g now, so I'm using g instead of f. G of x plus delta x minus g of x over delta x. Okay, so I can do some side work. I'm going to skip that part. But g of x plus delta x, I just replaced this x with x plus delta x. And now I minus g of x, that's x plus x minus 1, radical x minus 1 over delta x. And now we're back to these questions that we did in chapter 3 with the delta x's, and you have to evaluate the limit. In order to evaluate this limit, I'm going to multiply by the conjugate of the numerator. So that would be radical x plus delta x minus 1 plus radical x minus 1. You're going to do that in the numerator and in the denominator. And when I full, because conjugates take out the oi in the fulling, you get x plus delta x minus 1 from your firsts, x minus 1 from your lasts. Notice how your teacher is being extremely careful about distributing negatives. And in the denominator, again, do not multiply this out. You only want to multiply out the conjugate in the part where you have a conjugate pair. The other part you want to leave alone because something's going to cancel. And so let's do our cancellation. X minus 1 minus minus 1. I have a delta x on top and a delta x on the bottom. That cancels, leaving nothing on top. Well, a 1 because I divided away the delta x. And on the bottom, x plus delta x minus 1, x minus 1, both of those in a radical. Now I'm going to evaluate this limit. Notice the only part where I have delta x is right here, and I'm just going to make him 0. So I have 1 over radical x minus 1 plus radical x minus 1. Oh, those are the same thing. 2 radical x minus 1. That is the derivative, g prime. Okay, and now I'm going to make you do this last rational expression right here. F is 1 over x plus 2. You're going to get an indeterminate form in which you have to get a common denominator there. Best of luck and happy studying.